Hello students, this is the fifth lecture of the function in which we will go through transcendental function. So as an example of transcendental function, one of them is inverse trigonometric function. We will focus ourselves on inverse trigonometric function, as inverse trigonometric functions are sin inverse x, cos inverse x, tan inverse x, and besides cosec inverse x, sec inverse x, and cot inverse x also. And we will go through properties of these inverse trigonometric function in detail. So basically, before this inverse trigonometric function, let's we come for transcendental function. As first is constant function. Fx, which is called constant function. Constant function is the function in which the range is only singleton set. Singleton set means there is only one element in the range, just like y equal to b. If you see here, constant function y equal to fx equal to b, where b is a constant. Just like example, if we take y is equal to fx equal to 2. 2 is the function here. This is constant function, So you see, this is a constant function, comes like this. If we draw the graph here, as this is x-axis and this what you call y-axis. This is the line y equal to, suppose any constant, if we write y equal to 2. So y equal to 2, at every point you find this is 2 here. So this is constant function. You see, if we say something else like y equal to -3, then this is also a constant function. So you see here, this is x-axis and this what I call y-axis, and here the line y equal to -3. This is a constant function. Suppose somehow if we take another example like this one, y equal to mod of x plus 2. You say here, that is mod of x plus 2, right? Y equal to mod of x plus 2, and here plus mod of x minus 3. Mod of x minus 3. So this is the critical point here, that is -2. Here the critical point is, this is -2, as you see. So if we draw the graph here, this will be -2 somewhere and this will be 3 somewhere. So between -2 to 3, if you analyze it, the graph is, that is 1. So this is a boat shaped graph. This length is 1. So here if you see, for every value of this one, for every value of x lies between -2 to 3, that is for every value of x belongs to -2 to 3 close interval, you find x y equal to 1. Now, which is the function here? You see here, between -3 to 2, that is y equal to 1. So this is also said to be constant function. Let's take some more example. Identity function. Identity function is the function, you say y equal to x. Y equal to x is a line which is simply, it's nothing, it is a y equal to x is a line, that is, you say here y equal to x, what we call simply a straight line. A straight line making angle 45 degree from positive x-axis, that is called identity function. Means at every x you will find same y. The domain is also a real number, the range is also a real number, and it making angle 45 degree from positive x-axis. You see here, from positive x-axis. Here the angle is from positive. This is 45 degree angle. Okay, fine. So, and that is also called bisector of first and third quadrant. Here it is bisecting first and third quadrant, as it is 45 degree angle. Now we'll focus ourselves on inverse trigonometric function, which is the transcendental function. So here in inverse trigonometric function, the basic 6 inverse trigonometric are sine inverse, cos inverse, tan inverse, and cosec inverse, sec inverse, and cot inverse. So we will discuss the graph, domain, and range in detail. But before to just get any idea of inverse trigonometric function, we will focus ourselves that here how inverse function attains. For any inverse function, a function should be bijective. If the function is bijective, then only its inverse exists. But you know, all trigonometric functions are periodic in nature. As in the period chapter, we have already discussed, the period is never be bijective. Why so? Because it doesn't follow all bijective function should follow injective as well surjective. But in case of trigonometric function, as it is periodic, so it is never be one function. It is, you know, that is many one function. It is here always many one function. So its inverse is not possible, you can say. You say its inverse is not possible. To find its inverse here, we have to make it bijective under some certain condition. How? Let's see. So sin x is when sin x, if you check the graph of sin x over here, like see, let's see the sin x graph, y equal to sin x, y equal to sin x. We draw the graph of sin x. Here this is the sin x. But here you see this is periodic function. As if you draw a line parallel to x-axis, it cuts several points. So it is not one function. It is many one function. Many one function. It is many one function. So to be one, we have to consider the part where it is one. Let's see where it is 1. So if you see here, from this point means up to pi by 2, from minus pi by 2 to plus pi by 2, if you see this red part, then this function is said to be 1 function, because beyond this, as this is, you say pi by 2, and here it is say minus pi by 2. So between minus pi by 2 to plus pi by 2, in this region, if you see, the function is 1. But beyond pi by 2, if you see here, beyond pi by 2, then between in beyond pi by 2, this is wrote on pi by 2. So beyond pi by 2, here the function molds and it attains same value as entire sin x ranges -1 to +1. So we have to analyze between minus pi by 2 to plus pi by 2, as x and y interchange in the case of inverse. So you see the range is here -1 to +1, it will behave as a domain for sin inverse x, and hence we see sin inverse x graph. So the domain of sin inverse x will be -1 to +1. Domain of sin inverse x will be -1 to +1, you know, and range its corresponding value minus pi by 2 to plus pi by 2. So its principal value branches minus pi by 2 to plus pi by 2. So the graph exists like this way. So this is the graph of sin inverse x, you see, minus pi by 2 to plus pi by 2, this part. This is also the reflection of, you know, y equal to sin x with respect to y equal to x line. If you see here, then let me draw y equal to sin x first. Y equal to sin x. So you know, this is sin x graph. You see, this is sin x graph. Okay. So if we draw a line y equal to x here, this is the line y equal to x. Okay. So if we take a mirror image of this with respect to this line, this green line, which is y equal to x, so we will find this is the sine inverse x graph. So this white portion will be as a sine inverse x part, which is the image of this part only, up to this part only, up to this part. So we will recall here, as we are taking the image of this portion only, and here this portion only. So this is the sine inverse x graph, y equal to sine inverse x. So the graph is here, white portion is y equal to sine inverse x. Here sine inverse x means not 1 by sine x. Sine inverse x is, this is the inverse function, you know. So this is the graph of sine inverse x. So its principal value is, you see, minus pi by 2 to plus pi by 2, and domain is minus 1 to plus 1, which was the range of sine x. Similarly, cos inverse x also. So you see cos inverse x graph is here. The range is 0 to pi, and the domain is minus 1 to plus 1 here once again. So you see here, this is also the reflection of y equal to cos x under the condition of x belongs to 0 to pi, because in this only between 0 to pi only cos x you find that the function is you say 1 function, so that it becomes bijective. So let me draw the graph of cos x over here. So let's see, this is the graph of cos x, you know, this is the graph of, we say, cos x. This is the portion of cos x. Okay, this is y-axis, and this what you call x-axis. Now if you see here, this point is pi by 2, this point is pi by 2, and this point is, you know, that is pi here, and this point is 0. At 0 the value is 1, So if we notice this point, that here in this part up to pi, then means only this part, what the green part is going on here. This part is, if we consider this part of the cos x only, then we find it fulfills the behavior of 1 and this one injective and surjective onto function, as it lies between minus 1 to plus 1. The range will be also minus 1 to plus 1. So if we take the graph here, this one, if we take the mirror image with respect to the line y equal to x. So with respect to the line y equal to x, if we take here the mirror image with the red color, we will find the graph of cos inverse x, you know. So this 0, 1 point we will get here, that is 1, 0. That will be the image here, 1, 0 of this point. Of this point we will get the image here. So for this very graph, we will find this part of the function, right? And this is the 0, 1 point. And for this part where I am putting the red dots, the image will like this way here, as this is pi by 2. So pi by 2 is 1.57 nearly, somehow like this way we will find, and like this way. So this red portion is the graph of cos inverse x. You see here the red portion is the graph of cos inverse x. If we draw over here like this, the graph of cos inverse x. So this is x-axis, this is what you call y-axis finally. Anyhow, so we see the graph is, red portion is y equal to cos inverse x. Okay, so you see cos inverse x, this is the graph here. This is the sine inverse x and cos inverse x. Let me revise it. Domain lies between minus 1 to plus 1. Range is minus pi by 2 to plus pi by 2. Here in the cos inverse x case, 0 to pi, and domain is once again minus 1 to plus 1. Mind this point, notice to be here that domain of sine inverse and cos inverse are same, as the range of sine and cos are same. So we find that was -1 to +1, and the range of sin inverse x minus pi by 2 to plus pi by 2, and range of cos inverse x is 0 to pi. Okay, let's come for tan inverse x. So y equal to tan inverse x. If you see tan inverse x, then the range of tan x is, that is all real number, and the domain of tan, that is not defined for or pi by 2. So when we consider the tan x graph between minus pi by 2 to plus pi by 2, that which is the principal value branch, so the here it consists as 1 1 and 1 2 function, and it will become bijective. So tan x, when it is bijective, x lies between when it is minus pi by 2 to plus pi by 2. So that will become a range here on the corresponding value, and the entire range of tan x will become the domain of tan inverse x. So the domain of tan inverse x will be the all real number, and range of tan inverse x is once again, let me notify here, domain of tan inverse x is all real number, and range of tan inverse x will be minus pi by 2 to plus pi by 2. At minus pi by 2 to plus pi by 2, it won't take the value, attain the value minus pi by 2 to plus pi by 2. It shows the asymptotic behavior as x it approaches towards infinity. Here it approaches towards pi by 2, means it is open interval, you can say, minus pi by 2 to plus pi by 2. That is an open interval of tan inverse x. So let me draw the graph of tan x to make a complete understanding over here. The graph of tan x here, like this. This what I call x-axis, and this is here y-axis. And let me draw with the green color of asymptotes here. These are the point here, roughly I am sketching pi by 2, and here that is somehow minus pi by 2, we can say, and later on we can recall this pi as here once again 3 pi by 2, you say, and here that is minus pi, and one can recall like this way also, right? That is fine, minus 3 pi by 2. Let me complete this. So if you see the graph of tan x is, I am drawing tan x, tan x graph is like this. In the first quadrant it's positive, and the third quadrant is still positive. So here in the third quadrant, once again pi by 2 to pi by 2 to pi, that is pi by 2 to 3 pi by pi to 3 pi by 2, pi to 3 pi by 2. Between pi by 2 to pi, the graph like this way, and here the graph is like this way. Correct. Now minus pi, you can say here, that is minus pi. So if we draw the graph here, we are interested to draw the graph of tan inverse x, then let me draw the line y equal to x over here. Here the line, that is y equal to x line. Okay. And now we will take the mirror image with respect to this line. Mirror image with respect to this line. So if we take the mirror image here, then what we find here, that is these green lines will go like this way here, and this part of the green line, which is in minus, passing through minus pi by 2, here it passes like this way. So with the red color we will draw the graph of tan inverse x. The part which is, I am putting once again red dots over here. So with this part we have to take the mirror image like this way, and for this very leaf we will, with this leaf which I am putting red dots, so we will take the graph like this way, which is just about to touching these green dot lines. So here the red leaf of this portion is the graph of tan inverse x, we can say. This is the graph of tan inverse x. This is the graph of tan inverse x. Fine. So if this is the principal value, although this such red leaves will also beyond pi by 2 and minus pi by 2 means 0 comma pi by 2. This point is, this is 0 comma pi by 2 on the y-axis. You say 0 comma pi by 2, one can write over here, or 0 comma minus pi by 2 you can also say. Let me erase this because figure will become dirty. So here once again, and we will find the graph of tan inverse x. Now come to the point. Let's see over here. This is the graph of tan inverse x. Similarly, we will go for y equal to sec inverse x also. In the sec inverse x, domain of sec x is minus infinity to minus 1 union 1 to infinity, and its range is 0 to pi, difference pi by 2. How this comes? As the domain of range of sec x was minus infinity to minus 1 union 1 to infinity, and the point where sec x not defined, that was odd pi by 2's. So within the interval 0 to pi, which is the difference pi by 2, we have to notify that the function is bijective. So let me recall this properly to get complete understanding. First of all, we will draw the graph of sec x. Okay. So for sec x, you have to draw the graph of cos x. So let me draw the graph of cos x by like this. Okay. To get the more information about here, more accuracy, you can use the app known as Desmos. In Desmos also, if you plot here, you will get the complete plots of any type of curve. So wherever the cos x comes to the point, wherever the cos x vanishes here on x-axis, we will draw the asymptotes. These vertical dot lines, these will behave here as asymptotes here. So, and with the help of this green lines, we will lift this graph of sec x. These cups are sec x graph. Okay, so in 11th class we have already discussed more about trigonometric functions. So you can go through and make a revision of trigonometric functions, trigonometric graphs. There we told about how to draw the sec x graph. This is the graph of sec x. Now we have to consider the point once again. It's a periodic function, as it is you saw not 1 1, it is many one function. If you draw a line parallel to x-axis, it cuts several points, so that it's not a that is not a 1 1 function. It's not bijective, so we can't find inverse. So we have to restrict ourselves to within some certain condition so that it becomes bijective. So to make it bijective, what we have to notify is from 0 to pi by 2. 0, and this point is pi by 2. This point you say pi by 2, and this point you say this is pi. Let me erase this part because figure will become dirty. And here we will draw the line y equal to x to make the mirror image here. Okay, fine. Y equal to x. So if we see over here, this point is 0 to pi by 2, 0 to 0 comma 1. So here 0 comma 1 is somewhere here. Okay. So this is pi by 2 point where cos x vanishes. So here will be also somewhere pi by 2 point. So let me draw this first of line pi by 2, and here also this is minus pi by 2, this part. So yes, so this is this point is 0 comma 1 and this point is pi by 2. So we have to find 1 comma 0. 1 comma 0 is somewhere here, 1 comma 0. Okay, so for 1 comma 0, what we say here, 1 is less than pi by 2. This part is 1 comma 0, and we will take some another color, red color at least, to make it pi by 2. So for 1 comma 0, what we see, we will go like this way. The graph comes like this way. This is the image of this portion, this portion where I am shading this green part with the red dots part. This is the mirror image of this with the line y equal to x. I have not written y equal to x line. Let me write y equal to x line, for which we are taking the mirror image as this is a mirror line, and this red part is the mirror image of this green portion which is on the red dot, which is hovered over a red dot. Now we will hover over red dot over here, so to make the mirror image with this part, so it will behave like this way between, as this is the graph of sec inverse x we are plotting. This is the sec x graph, and green part is sec x graph, and this is one part 0, so we won't go like this way minus pi by 2. We have to come on this pi portion, where this pi portion comes from. So at pi, this is behaving as minus 1, this part, so we have to cover over this portion which is in here 4th quadrant, so we will find in 2nd quadrant with respect to the line y equal to mirror image here. So we will go and take the image of this portion. This part, this part is this coordinate is pi comma minus 1. So pi comma minus 1 in pi comma minus 1 in the this one for mirror image with respect to the y equal to x line, this will become minus 1 comma pi. So where this minus 1 comma pi comes here, minus 1 is somewhere here, so minus 1 comma pi is somewhere here above pi by 2, and this is somewhere pi means nearly 3.14, so this is pi. So here let me note down this part here, that is pi, this portion is pi, this portion, this length is pi, so up to this length we have to take this length. Here we are taking the mirror image of this point. I'm going to make a green point, this point here, this is the mirror image, this point to mirror image of this point. Now once again we will use red color for image of this portion, which is a red dot hover over green lines. So we will take this mirror image here, this was minus 1, so from minus 1 to pi by 2, this portion is here, that is pi by 2, this portion is pi by 2. So this red, once again I am plotting overlining over here, this part and this part is the graph of sec inverse x. Further part will be also considered as a sec inverse x graph, but it doesn't follow the functional definition rule. So we have to come over here sec inverse x. Let me check the graph here, sec inverse x. So this part we have already plotted from 1 up to it is approaching towards infinity, and here that is pi, and here pi by 2. At pi by 2, that is the asymptotic behavior. This is the graph of sec inverse x. Okay, fine. So let's see of the another graph. So come to the graph of cosec inverse x. What is cosec inverse x? Similarly, as like in sec inverse x we have discussed, we will go for cosec inverse x also. Cosec inverse x, the domain is once again that is same as like sec inverse x, and the range will become here between minus pi by 2 to plus pi by 2, close interval, difference 0, that you say. You can try also by taking y equal to x line mirror image, and if you won't get an idea, then I will discuss it in detail further. Similarly called cot inverse x also, as like tan inverse x, here cot inverse x, but basically you have to go for domain and range. Domain, range and principal value, that is between 0 to pi, this should be by heart. You can see the graph also here, cot inverse x. Point to be notified over here, better just to make a complete understanding of these inverse trigonometric function, you can make a table over there for the domain, range and graph, And one thing is to be noticed here, that the function which are sine inverse x, you see tan inverse x, and one of them is, that is cosec inverse x here. This one, fifth portion, fifth graph, cosec inverse x. Not graph. These functions are actually inverse trigonometric functions. All the inverse trigonometric functions are nothing. These are angles. So these angles, sine inverse, tan inverse, and cosec inverse, these angle shares first and fourth quadrant. And rest of the three function, that what we call cos inverse x and sec inverse x and cot inverse x, if you see the graph here, always it is above x-axis. So not graph. These angles means these functional values, these which are the angles, these angles shares first and second quadrant, because their ranges are from 0 to pi. Here you see cos inverse x, cot inverse x range is 0 to pi. If you see the cos inverse x range is also 0 to pi, close interval. And if you see the graph of the value of sec inverse x 0 to pi, difference pi by 2, then these ranges are between 0 to pi. So they are sharing first and second quadrant. Although you should notice that third quadrant is never used in inverse trigonometric function. So that is very important point. We say third quadrant is never used in ITF. In entire ITF chapter, we won't use third quadrant. That should be noticed. So come to the point over here. So let me summarize this table, what we studied over here. You can also draw it and write down this properly. This is very important. Besides this, as in this table, I have only collected over here domain and range. One more column you can draw, and you can draw the graph. One more column you can make here and draw the graph also, to just make it in fingertips. Let me recall it once. Y equal to sine inverse x, domain is -1 to +1, range is minus pi by 2 to plus pi by 2, correct? And graph you can see over there, right? So y equal to cos inverse x, domain -1 to +1, range is 0 to pi. Y equal to tan inverse x, domain x belongs to all real number, range y belongs to minus pi by 2 to plus pi by 2. Y equal to cosec inverse x, domain -infinity to -1, right half close interval, union 1 to infinity, left half close interval, and y belongs to minus pi by 2 to plus pi by 2, close interval, difference 0. Y equal to sec inverse x, x belongs to -infinity to -1, right half close interval, union 1 to infinity, left half close interval, y belongs to 0 to pi, close interval, difference pi by 2, as at pi by 2 it's not defined. Y equal to cot inverse x, again domain x belongs to all real number and y belongs to 0 to pi. What we conclude over here, if you see what I was telling before this, if you see number 1, which is sine inverse x, number 2, which is tan inverse x, and here you say number 3, that is tan inverse x, and number this one, fourth, that is cosec inverse x. These three functions shares, you have to see in the range column. Go in the range column, first one, now third one, okay, and then after this one, fifth one. If you see, sorry, not fifth, fourth one. Fourth one, okay, sine inverse x, tan inverse x, and cosec inverse x. Here you can see this is minus pi by 2 to plus pi by 2. Here also minus pi by 2, plus pi by 2, minus pi by 2, plus pi by 2. Sine inverse, cos inverse, sine inverse, tan inverse, and cosec inverse share first and third quadrant. These shares first and third quadrant. let me write over here, first and third quadrant, first and third quadrant, right? First quadrant and third quadrant, these share first quadrant and third quadrant here. Okay, let me erase it because we have to write some more things. Then after, and rest three functions, what do you see? Rest three functions, that is cos inverse, and here that we say sec inverse, cos inverse, sec inverse, and that is cot inverse, that is cot inverse. These three function shares here, these three functions 0 to pi, 0 to pi, as these three function shares which quadrant? First and second quadrant, first and second quadrant. Although the red one shows which one, sine inverse, tan inverse, cosec inverse shows shares first and third quadrant. Although this is here, all trigonometric functions are common in first quadrant. In first, they shares all inverse trigonometric function shares first quadrant. But from this range, the result of range, you can conclude that, we can conclude over here, third quadrant is never in use. So that is very important point. So you can note down also, third quadrant is never in used in ITF chapter throughout. So let me take example of this question. So if I say that tan inverse x here, tan inverse x equal to, you say, tan inverse x equal to, if you say here, that is 5 pi by 4, 5 pi upon 4. So what the value of x you will code? What the value of x you will provide here? That is tan inverse x equal to 5 pi by 4. Some student can solve x equal to tan 5 pi by 4, tan pi plus pi by 4, and tan 180 plus theta. They say that this is third quadrant, and so we can say tan pi by 4, then they will say that value is 1. So x is 1. Is it correct? So x equal to 1. Is this answer correct? X equal to 1. Or you say tan inverse 1 can be 5 pi by 4 also. No, this is a wrong answer. Let's see. Because tan inverse x, if you see over here, tan inverse x shares which quadrant? First and last quadrant, minus pi by 2 to plus pi by 2. So tan inverse x, not only tan inverse x, any inverse trigonometric function doesn't share third quadrant. So if we say tan inverse x here, that is 3 pi by 4, if we say tan inverse x here 3 pi by 4 also, not only 5 pi by 4, if we say 3 pi by 4, let's say, let me write 3 properly, 3 pi by 4, then what we say here, x belongs to no solution. X belongs to no solution, phi. You can see. So here what we conclude, that no inverse trigonometric function shares third quadrant. So sine inverse x, tan inverse x, let me revise once again, sine inverse x, tan inverse x, and cosec inverse x shares first and fourth quadrant, and that is minus pi by 2 to plus pi by 2, right? But cosec inverse x doesn't follow 0, and here cos inverse x, sec inverse x, and cot inverse x shares first and second quadrant. Okay. Let's say some properties of inverse trigonometric function. So we will go for sine inverse sine x, and tan inverse tan x, and cot inverse cot x later on in the next lecture. So in the next coming lecture, we will go for T inverse of Tx and T of T inverse X and more property about inverse trigonometric function. We will focus our entire attention on inverse trigonometric function with different illustration also. So be ready to just watch another coming video for another coming lecture, which will be the lecture 6, you can say. And also we will in successive lecture in next coming lectures, we will discuss in transformations of graph in detail. Y is equal to f of gix, gi of fx, y equal to f of fractional part of y equal to fractional part of fx, or any type of function which is in the form of any transformation with shifting and of any function of function, and detail in composite behavior also. So keep watching, and besides keep your studying well. And once again, I will just emphasize on this: just draw the table of inverse trigonometric function to thorough the domain, range and its graph. Thank you.